Okay. Okay. Good afternoon, everyone. I think we can start now. So just let me know whether you hear me. I just make sure that I am not mute or you cannot hear me. So do you hear me? Okay, good, good, good. So I think we can start now. Yeah, today good day anyway. Yeah, we can free day. We can we don't need to wear a mask outside, and we can gathering now. Okay. So anyway, yeah, we back to the this week tutorial. This week lecture. Okay. So this week we will learn about dynamic programming. Yeah, indoor still need the mask, but outdoor at least yeah you can go to the park or anywhere. You can don't need to wear mask. It's better than previously. Okay. Anyway, yeah, back to the lecture. So this week we will learn about dynamic programming. Okay. So why the dynamic programming? So we start with the Fibonacci sequences. So I think most of you will know about the Fibonacci, right? So it's just a sequence so that the value of one their function, or yeah, the number at the position n will be the sum of the previous two number, and the base case is like f0 is 0 and f1 equal 1. Okay. So the sequence will be look like this. Like for example, I think something wrong here. Okay. So anyway, yeah, something like 55 is the sum of the 21, 34. I think something wrong here. Yeah, it should be they know 4 here. It should be, yeah, 5 is sum of the 2 and 3. Yeah. And 3 is sum of 2 and 1. Yeah, one number will be the sum of the previous will be equal to the sum of the previous two number. Okay. So yeah, this one I think very famous one, Fibonacci one. So for calculating the Fn, right? I mean, one of the easiest way is just do the recursive algorithm, right? This is the one pseudocode for the symbol for this Fibonacci to calculate the Fibonacci at the position n. Then we just there's a base case, right? F0 equals 0, F1 equal 1, and then Fn will be equal Fn minus 1 plus Fn minus 2. Okay, you can run this one and you can easily get the number at the position n. Okay, but this one has a problem. So this function, this algorithm has one problem. It's a very serious problem. So what's the problem here? I think if we look at this, right, I think it's very straightforward, right? It follows exactly the Fibonacci definition. So what's the problem here? So if you look at the recursion tree, then you can, you can, find out the problem. Okay. For example, if we are looking at the, we are calculating the Fibonacci 5, then like the definition, right, is the sum of the Fibonacci 4 and Fibonacci 3, right? Yeah, it's just a definition and like exactly like what we are doing, like the recursion function, right? Then recursion Fibonacci 4, we call Fibonacci 3 and Fibonacci 2. And similarly, 3 will count 2 and 1, and 2 will count 1 and 0 because they are base case, so they are just 1, 0, right? 1, 0. So, but if you look at this, you can see the problem here. That's it. We have many subproblems that are overlapping. For example, you can see here, we had a Fibonacci tree. Here we also have the Fibonacci tree. Then to calculate the Fibonacci tree, we need to count Fibonacci 2, 1, blah, blah. But then later we face with the Fibonacci tree, we still need to recalculate Fibonacci 2 and 1. And you can see a lot of, the the overlapping. For example, you have so many Fibonacci 2 here, right? Then whenever we face with the Fibonacci 2, we need to recalculate again, right? According to this function, I mean this recursion tree. So this is the problem, serious problem, because we need to recompute so many things that we already computed before. And if we are using this algorithm, right? So what the complexity? You can see like one count Fibonacci and you will count the other two, right? And they are just like the tree, right? One every parent will almost count two, right? Two childs. So the complexity will be about O to power n, correct? And this is the huge complexity for this particular algorithm. This one very clean, very clear, very clean, very easy to understand, right? But yeah, this is the O(n), O to power n. And we need to, I mean, recompute so many things that we already know, right? So whether we can have any better solution for that, or any best solution that so that we can calculate it in O(n) instead of O to power n or not? Is there any algorithm that we can do in O(n) or not? So that's the idea of the dynamic programming. So why the dynamic programming? Dynamic programming is just the recursion like we have before, right? We have the recursion algorithm, right? Plus the memoization, okay? It's just like recursion plus the memoization. So recursion, like we know, right? The problem can be solved recursively like the previous algorithm. But we have the new things, we call it the memoization. So what the memoization mean? It means that we store the optimal solutions to the subproblems in a table or in memory or in cache or whatever. It means that we have some mechanism to store the subproblem solutions so that later we don't need to recompute again. For example, you can look at this, right? If we calculate the Fibonacci 4, we need to calculate the Fibonacci 3. Then later, if we face with the Fibonacci 3, right? Do we need to recalculate? No need, right? Because actually value are the same, right? So if we know the value here, then we just reuse here. We don't need to do the recursive count, okay? So that's the idea for the dynamic programming. Dynamic programming, the only difference with the recursion is we have some mechanism for memoization, okay? Or we have something, some memory, some table, some cache to store the some subproblem, some value of the subproblem that we calculate before, okay? So the idea very simple like that. So it's just similar to the divide and conquer, like we just mentioned, right? We break the big problem into the subproblem. Like for example, if we calculate the Fibonacci 5, then we need to calculate Fibonacci 4 and 3, right? So we break it into the subproblem. And we solve the subproblem recursively, like we mentioned, I mean, the previous algorithm, right? And we combine the solution. This is the divide and conquer. So, but why the difference between the knife divide and conquer and the dynamic programming? Let's say for the dynamic programming, right? It can be applied when the subproblems are not independent. Like we just mentioned, right? We have so many things that correlated, or you can have something like repeatedly, okay? So that's every subproblem is solved once only and saved in a table, okay? So that we don't need to recompute again when we face this subproblem again, okay? So the problem usually have a multiple solution, multiple optimal solution, right? But for the dynamic programming, right, it may just return one of them, okay? So the dynamic programming is not used to find all the optimal solution if there are many suboptimal solutions. So it's only suitable if we only need one best solution, okay? It's not the algorithm that we use to find all the optimal solution, okay? if we have so many optimal solutions. So this one only used to solve one, okay, to find one optimal solution. Okay. Then like I mentioned, right, the dynamic programming apply when the subproblem are not independent. So it means that if the subproblem are independent, so the dynamic programming is not useful. It's just like similar like divide and conquer. But if the subproblem, like we don't have, like for example, we calculate the F4 and F3, right? If the F4, F3 doesn't have any dependent, like if you want to calculate F4, we need to calculate F3 and F2. Then we have the dependent, right? Because to calculate F4, we need to calculate F3. Then we also have the F3 here. So that is the dependent. But if on the subproblem are independent, like we have the recursion tree on component are independent, then the dynamic programming is not useful. Okay, so this is some note for the dynamic programming. Dynamic programming usually very good, but it not best in all cases. For example, it cannot, it may not find all the optimal solution if they are, okay. It just find one, okay. And if the sub problems are independent, then we cannot apply the dynamic programming. We need to apply the order as well, okay. So for the dynamic programming approach, we have two ways. That is the top-down approach and the bottom-up approach. So what the top-down approach mean? Top-down means that we recursive using the solution to each subproblem. For example, we start from the, for example, F5, right? Then if we calculate the F5, we need to calculate the F4, F3, okay? So we memorize the, the top down, and then later if we face with, later in the subproblem, the child subproblem, then we just reuse. But we calculate from top to the bottom, okay? Then we memorize the solution to the subproblem and reuse them later. So this is a top down, okay? For the bottom up, they are different. Bottom up, we calculate from the bottom up to the things. So we solve the subproblem first. We solve the base case, and then we form up with the bigger solution. Okay. To just combine the subproblem into the bigger. Then yeah, some of you may ask whether we know when we use the top down or bottom up. Actually, both approach. Normally you can use. I think there are not much differences, but there's some special. The case. It depends case by case. We look at the way we calculate. But normally, most of the dynamic programming problem, you can use both top-down and bottom-up. There are not much difference, okay? Not much different, okay? Except there's some very, special one. It depends on the case by case, very hard. But normally for the dynamic programming, we look into the problem and see whether we can apply or not, okay? Because we need to look at this, see whether any overlapping in the calculation, anything we can reuse or not. Okay. So hard to say. Yeah, but most of the case we can use both top down and bottom up. Okay, and normally the complexity, most of the case they are the same. Okay. Okay, so for that, it's just a theory, right? We go to the real problem, like the Fibonacci problem. Okay. So we look at the Fibonacci again, okay? So what the top-down approach mean? You remember, right? When calculate the 5, we need to calculate 4 and 3, right? And to calculate 4, you need to calculate 3 and 2, right? Right, for Fibonacci, okay? 3, you need to calculate 2 and 1, okay? So for the top-up approach, right, we start from the top, okay? So we start with 5, okay? But remember, for the dynamic programming, we need to have a memory, okay? So therefore, for this approach, right, we have the we keep an array, okay, to store the solution. For example, this is the storing for F0, the value for F1, value for F2, value for F3, F4, blah, blah, something, okay? Then we store an array and we initialize all the thing is -1. It means that we don't know, right? Then when we calculate top down, we calculate Fn, right? We calculate Fn, okay? So of course, this one is a base case, right? So we start a base case. So for example, if n equals 0, then we just replace this with the 0, right? Because we know that f0 is 0, right? So we just fill the value of base case. F1 equal 1, so it equal 1. Okay. So this we already know. Then how we do? We check because we know that fn equal fn equal fn minus 1 plus fn minus 2, right? So to calculate the fn, of course, we need to calculate fn minus 1 and fn minus 2. But like we mentioned, right, because this one is to store the value for the fn, right? This one store the value for f0, this one for f1, this one for f2. So to calculate the fn, firstly we check the table first. We need to check this table whether we have the value for fn minus 1 or not. Okay, so we check the table. So we check at the position n minus 1. For example, position n minus 1. Okay, we check the position n minus 1. If it already calculate, it means that the value will be different from 0, right? So we check if this one equal minus 1, it means that it has not been calculated yet, right? So it means that fn minus 1 was not calculated. Then we just call the recursive function to calculate, right? We call the recursive function, and then we start the value in the position n minus 1. Okay, so it means that if it has not been calculated, okay, we just calculate and then start the value in the n minus 1 here. Okay, so start some value here. Similarly, right, we check. We check for the fn n minus 2. If it not calculate yet, then we call the recursive function to calculate, right? To check whether calculate or not, we just check the position n minus 2, right? See whether equal 0 minus 1 or not. If not equal minus 1, it means that it already calculate and store. Then we use. Otherwise, we just do the recursive function to calculate it and store it in the value. Okay. Then if they are both calculate, right, then we just calculate the m. We use the value in the table, okay, to add it. Okay. Then we store it in the mn. Mn means that the position n, right? Okay, the position n. Then we start here. Okay. Then after that, we just return the mn. Okay. This is they call the top-down one. Then later, right? Later, if we face the fn again, you don't need to calculate, right? Because you know that n different. Mn already calculate because their value stored in the table. Okay. So you see the array here. It's just because I just draw the array. In the general case, it's not about the f5 or f things, right? I just store it. If later, right, if the question asks you to calculate the f100, then of course you need to create the array of 100. Okay. How do we prevent? Actually, this one is outside the Fibonacci. Outside the dynamic programming. This one you store it locally in the main function or in things. You just store one time, and it will store the value for the on the Fibonacci number. Okay. So some of you may ask, how can we know the size, right? Then it depends. Then we store it dynamically, right? So like for example, you in the main function, right? You can ask, okay, what is the value for which fn? What is the value of n, right? Then if the user type 1000, then you dynamically allocate the memory 1000, array of 1000. Okay, for example. Okay. For the array, we store it in the global scope. Okay, then on the Fibonacci will fill in this array. Okay. So we just create one, one array globally. Okay. So yeah, that's the way that we can use a Fibonacci. And then you see, right? Sorry. For example, after this one, right? For example, okay. So I will do. For example, if we call the Fibonacci 5, right? Then firstly, it called the Fibonacci 4 and Fibonacci 3. Okay, of course, based on this one, right? And because of Fibonacci 4 at the start, right? Fibonacci 4 has not been calculated, so we call the Fibonacci 3 and Fibonacci 2, right? And 3 will have, because all the value are -1. Okay, I erase that. Because at first we only have the two, at first we only have two base case, right? 0 and 1. So we know that M0 and M1. Then 3 will count 2 and 1, right? Then 1 will count 1 and 0, okay? Okay, up to now, right? We know that, okay, 1 and 0, because M1 and M0 already have the value. Then we just know, so we know that M2, right? So M2 will be the M1 plus M0. So M2 will be 1. So we fill the table 1 here. Okay, correct? Then we go back, right? Because they are the recursive comma, right? So F3 will call F2 and F1. F2 return 1 here. The F1 also return 1, right? So then the F3 will be the return what? Return here, right? So it will be the M2 plus M1. M2 is 1, M1 is 1. So now we have the value for this one is 2, right? Then we fill in the 2 here. Then we will return 2 here, right? Then we go back here, right? So for con 3 and 2, but 3 have value 2. F2 also had a value, right? We just check in the table. We don't need to recalculate 1, right? F2, the M2 is 1. M3 is 2. So this one, so M4 will be 3. Then you fill in the table 3, right? So this is the way that, the recursive function call. Then you finish the M4 with the value 3, right? You fill in the M4 is 3 here. Then you go to M5, right? M5 is the M4, right? M5 is the M4 plus M3. And M4, M3 already have here. Then we just fill in. So actually, this one you don't need to call, right? Because you already have M3. 3 you already calculate here. So M3 is 2. So M5 will be 5, right? Then you fill in 5 here. Okay. Then if they just ask the Fibonacci 5, then you can return 5. They are final value. But you can see, right? A lot of things we don't need to recalculate, right? We recalculate one time. That's it. We calculate 2. Then later we file 2 here. We don't need to recalculate. We just use a value. Or 3 here, right? We calculate F3 is 2. Later we face the F3. We don't need to call the recursive. We just use a value 2. So that's the way that we can use the memory to accelerate the algorithm. We don't need to recalculate. We just, whatever we calculate, right, we store in the table. Then later we face this, we pick up. So how we know that we calculate or not? We just check. We look at the table. If the table different than -1, that it already calculate, then we don't need to call the recursive function, right? If they are different than -1, then we don't need to call this recursive function. Similarly, if already calculate, then we don't need to call this. So we just do the adding directly. So we just get the value in the array, then add it. We don't need to call the Fibonacci. Okay. If they're already there, if the value of n-1 and n-2 already calculated, then we just use. Don't need to call the recursive function again. So that is the idea of the dynamic programming. Okay, this is the top-down approach. Okay, for the bottom-up approach, we calculate from the bottom because we know that okay, calculate 5, we need to calculate 4, 3, 2, 1, 0. Then we calculate 0, 1, 2, 3, 4 first. Then we calculate 5. So how to do that? We know that okay, 0 is 0, right? So we just fill in the table. We also store the array. Okay, so 0 is 0, 1 is 1. So we fill first. Okay, then we go up. Okay, from 2. Okay, because 0 and 1 we already calculate, so we start from 2 until n. Okay, because n is the one that we want to calculate, right? So we start from 2. So the for loop will for from I equal to up to n. Okay, in this for loop, you see, from 2. So we start with 2, right? So m2 will be equal m1 plus m0. So m2 will be equal m1 plus m0. So it's just 1, right? 1 plus 0. Okay, 1. Then we loop again, right? I equal 3. 3 will be equal 2 plus 1, right? 3 equal 2 plus 1, so it will be 2. Okay, right? Then the for loop will continue. I equal 4. 4 will be equal m3 plus m2, so it will be 3. Similarly, I will go to 5, right? Then we just calculate m5 will be m5 will be m4 plus m3, yeah, 5. Then if the main program asks us to just calculate Fibonacci 5, then we can stop, right? Then we just return m5. Yeah. So it means that we know that we need to calculate 5, we need to calculate 0, 1, 2, 3, 4. Then we fill from the bottom. We fill 0 first, 1, 2, 3, 4, then 5. Okay. Then we stop. Okay. So what the complexity? Again, every time we just calculate 1, right? 1 time only. So complexity ON. Similarly, previously for this one, we also know that okay, every f, right, we only calculate 1. So the complexity also ON, right? Because for every f1, f2, f3, f4, we only calculate 1 time. Because later, if we face this again, we just reuse the value. So that's why we don't need to recall the recursive function. So complexity also ON, right? Okay. Because every time, every value of the f, we just calculate fi, we only calculate 1 time. So you can see, right? For the, using the dynamic programming, from the original complexity, if we use this original complexity, original algorithm, right? The complexity is ON, right? O to power n, sorry. The original one. Complexity is O to power n. But if we use the dynamic programming, we save a lot of things. The complexity now is just ON, because everything we just calculate 1 and we remember, right? So from O to power n, you have a new, much better. It's just ON. Okay. So you can see that the dynamic programming very powerful. Okay. But what is the disadvantage for the dynamic programming? That's the memory. We need the memory to store the value. But yeah, they are just a trade-off. If you need faster algorithm, then we need to sacrifice something. In this case, it's just the memory. But the memory here is quite cheap, right? It's just an array of the n. An array of the n elements. That's it. Memory that not enough. In this case, right? Unless you calculate the Fibonacci few billion or something. But here, if we just calculate the Fibonacci like 1,000, 2,000, then just create a 1,000 element array store. It's quite cheap, right? 1,000 array for the integer. It's just like if one integer is just 4 or 8 bytes, right? So 1000 is just 4 or 8 kilobytes, right? But 1000 here, I mean, if you calculate the F1000, right, you only need about an array of 1000, right? But here complexity is just O1, O-N, right? It just means that you just recursive 1000 times. But if you use the original, I mean the recursive one, right? You need to call 2 power 1000. And I think it run, I mean, for a billion years. Okay. With supercomputing, right? I think 2 power 1000 you need to run for a billion years. But now you only run for 1000 times. I think it's just 1 second. And you only need the array of 1000. That's it. Right. So it's super powerful. Yeah. So actually, right, later, I mean, when you finish the bachelor, you interview a company, right? Many companies ask this question. Dynamic programming is very important for the algorithm. You ask about hackers, they give limit memory, but of course you need to design it. Yeah. But I mean, the dynamic programming is a very common question when the interviewer interview the candidate. Yeah. Because for this one, you can, I mean, reduce the complexity a lot. You imagine, right? From 2 power n, you can reduce to on. Yeah, they say a lot. Okay, so we also have the other examples of the dynamic programming. For example, the string algorithm, like to find the longest common subsequence, the longest common substring, for example, 2 sequence, like 2 DNA, for example. 2 DNA, a string, right? Then how can you find whether they have the longest common one to, I mean, identify the relationship, for example? That is very important also problem. Or some algorithm like the Bellman-Fox, Floyd's. Later, if you study in the year 3, year 4, you can see this kind of algorithm. And also, for example, how do the matrix multiplication if you have the multiple matrix, right? If you design carefully, right, the complexity will reduce a lot. It makes faster. But if you don't have the better algorithm, right, you run forever. Yeah. And many problems can be used for the dynamic programming. Okay. Actually, for the both memory, I mean both bottom up and top down, right? I mean the memories use the same, right? Because you just create, I mean store an array, right? I mean, sometimes it some problem. If you can do the bottom up, then it's good. But sometimes you cannot design the bottom up, then you just call the top down. Okay. Because for the top down, if you see, right, for example, in this case, right, even though they call the recursive, but they call one time. Yeah. And it's just exactly like the complexity. Yeah. Just one time. Yeah. Okay. So, but I think this week we study about this. Next week we will study in details about the rod cutting and the knapsack problem. Okay. So this week we just learn about the definition of the dynamic programming, and I mean one example of the Fibonacci. Okay. One good question that how can I ensure that the technique like optimization will be tested in the lab, right? Very easy. For example, I ask you, okay, this is the Fibonacci. Ask you to do, okay, some student, okay, you may just do the recursive call, right? Then later, very easy how to test this. In the test case, right, I ask you calculate F1000. If you use the recursive function, right, your program will be stuck, cannot end, run for forever. For F1000, if you use the recursive one, use a symbol, this one, yeah, for sure it's stuck, right? 1000, then you need to complexity 2 power 1000, it run forever. But if you use the recursive one, it's just 1 second, less than 1 second. Okay. So very easy for me to test whether you use the optimal one or not. Because in the system, in the system, right, HackerUs, right, they have the limitation of the time. I can set 5 seconds or 10 seconds maximum running time. Otherwise, it return the running errors. Yeah. Okay. So I ask you, for example, Fibonacci. I ask you in test case 1000. Then I know whether you use dynamic programming or not. Okay. So yeah. So that's it. That's it for today. So you know about the dynamic programming and the Fibonacci example. So previous year we don't have this kind of previous year we still have. But 2 years ago we don't have this kind of the algorithm. And then some student later they graduate, right? They interview the company asked this question and they cannot answer. Then they claim back with voice, why you don't teach me this kind of the techniques during the university? So that's why this year, last year and this year, we included into the. Okay. So they are very important. Dynamic programming is very important for the programming. Okay, and I think the idea is very simple, right? You just store, keep a memory to store whatever you calculate. The idea is very simple. Why you need to recalculate again? Why you need to reinvent the wheel, right? The matching, let me see. The matching, the last one, right? The last one also the famous one, but the last one a bit complicated. So let me think, but it let me see whether I include, but if include, I just include only one question in the quiz. I don't test you about the programming, about the matching one. But the dynamic programming, I may test you. Yeah. The dynamic programming is simple, right? It's just storing the array and keep it. Matching, maybe I may not test it. I won't test you the programming. Okay. So the lab test 3, yes, I will make it 3 questions also. Okay. So for the matching, I won't test you the programming one. I will think whether I should include a quiz or not. One question into the quiz or not. But the question, MCQ question, if I include also easier. It's just about the idea. The store array is global. Yes, it's global. Okay, but you can allocate it dynamically, right? And after you finish the for example, finish the main program, you can release the memory. For example, after you calculate the Fibonacci n, right, you just release the array. Okay. So any more questions? Okay, if you have a question, you can ask me. Otherwise, I think that's it for today. Next week we will go to 2 more examples about the dynamic programming so that you know how to do. Yeah. Okay. Not next week. Next lecture. This is on Friday. Yeah. On Friday. For the top-down approach, we need the mn minus 2. mn minus 2 or mn is the same, right? We just 2 more memory. Okay. But mostly we still need the mn because we still need the m0 and m1. Later you see, then you don't need to top down. Yeah, you still need the m0 and m1 because later m2, right? M2 will be equal m0 and m1. Right? So still need the mn. Okay. Yeah. Like I mentioned, right? They both approach usually have the same complexity, but for some problem, you may not easy to calculate from the bottom. Then you may need to top down, or some problem you cannot calculate the top down. You may use. I mean, it's case by case. But in this course, most of the problems can be used both approach, top down and bottom up. Okay. Then for the test, right, you can do whatever, top down or bottom up. Okay. I mean, the thing that for the dynamic programming, it's exactly the one. It's just about you use the array instead of you directly call the Fibonacci. Call the recursive function. You just need the array to store and then some mechanism to check whether you already calculate or not. This one you need to calculate. You need to check because you do the top down, right? They sometimes you don't know whether you calculate or not. This one you don't need to check because you do the bottom up. So then you don't need to check because you know that when you calculate the tree, you already calculate 2 and 1 and 0. Yeah, so that's why you don't need to check. Okay. But some problem that you not easy to do the bottom up like this because this one is quite straightforward. Okay. Yeah, so I think that's it for today. Okay, see you this Friday. I only teach half of the course because they are the very big classes. So we divide into half.